And we're back. Welcome back from the weekend and happy Tuesday. Today we will be pivoting our discussion to mass storage. But before we begin, some administrative bits. The reading from the 22nd of November to the 25th, and then from the 30th of November to the 1st, will consist of sections 11.1 to 11.7. That's pages 449 through 472. Please take note. I don't include Thanksgiving break. That is for you to relax. As of today, including today, we have 3 class meetings left. Please be aware of key dates. The 25th, you are to vacate, if you're on campus, vacate the residence halls by 5 p.m. The 26th of November is Thanksgiving, followed by Black Friday. Please have a safe and happy Thanksgiving weekend, holiday. The last day of classes will be Thursday, the 3rd of December, reading day the following day. Our final exam period will be the 10th of December from 10:30 to 12:30 in the afternoon, during which you'll be doing project presentations. And then on the last day of finals, your projects will be due on the 11th of December by 8 p.m. electronically via Blackboard. So the objective of this module are to do fourfold to describe physical structure of secondary storage devices and their effects on the use of the devices, to look at performance characteristics, to evaluate some disk scheduling algorithms, and to discuss operating system services provided for mass storage. So let's take a look at mass storage. Now, whether you believe it or not, well, it's certainly true, magnetic disks provide the bulk of secondary storage for modern computers. Now, these drives, these magnetic disks, rotate about 60 to 250 times per second, so they spin very quickly. And we have a bunch of measurements that we talk about when we refer to their performance. We look at the transfer rate, which is the rate at which data flows between the drive itself, disk drive, and the computer. We look at the time that it takes to position the read and write elements, and so that means moving the disk arm to some cylinder, and that's called the seek time. And time for a sector on that cylinder, the track, to rotate around underneath the read-write head. That's called latency or rotational latency. And then, of course, if catastrophe strikes, you have a head crash, meaning it results from when your disk head, the read-write head, makes contact with the surface, and that's a pretty bad thing because you just destroyed your disk. These disks can be removable, and they typically are. And the drive for that disk is connected via some bus, and there are many different standards for that: USB, SATA, fiber channel, which is fiber optic, SCSI, and a whole bunch of others. There's a controller that the computer uses, and this controller sits and talks over the system bus to the disk controller that's built into the drive. And so there's a host piece that interacts with the drive part to give you the ability to store and retrieve information on your disk. And so in the early days, magnetic tape was the storage mechanism of choice, and this evolved from large spools to cartridges that contain smaller spools of this magnetic tape on which the information is stored. And this is relatively permanent, lasts for a long time. It can hold large quantities of data, but the problem is the access time is doggedly slow. Now, of course, the random access for a magnetic tape drive is 3 orders of magnitude slower than a disk, so it's very, very slow. But it's really good for large amounts of data that you're not going to have to access too much, namely backups. And so it's used primarily these days for backups and storage for infrequently used data, and also to transfer data, large amounts of data between systems. And so these magnetic tapes are kept in a spool, and they're wound with a motorized spindle to move that tape past the read-write head. Now, once that data that you get to that's wound up on the tape gets underneath the head, the transfer rate is pretty comparable to magnetic disks, but this mechanical winding and unwinding of the spool takes a lot of time. And so you can have pretty high storage capacity with these magnetic disks, which is why they are still around and very popular today. So this is a view of some pictures for your benefit of magnetic discs. At the top, we have a magnetic disc. So it looks like a large spool of plastic film material, and it's coated with magnetic coating. And when you energize the magnetic polarity on this tape in various orientations, north or south, you encode a 0 bit or a 1 bit. And so this is passed using a spool system, and here's a spool system. We have the tape going from one spool. We have the tape going from one spool into the read-write head onto another spool. And as the spool spins, it winds the tape and it goes past the read-write head. Now, in this picture down below, we have a closet with an archive of lots and lots of spools of magnetic tape. And something like this would store all of the data that you have on each of these tapes. And so that was how it's done. And by modern times, they've certainly reduced the size and increased the capacity with modern technology. And here we have our miniature spool, which is in a cartridge, which is how it comes today. And this cartridge is fairly high density storage. Now it's faster than it was back in the older days, but it's still slow relative to a hard drive. And here in the bottom, you see a picture of someone inserting one of these tape storage cartridges into a tape drive. And so you can buy them today. They're freely available. They only cost a couple $100 on something like Amazon. And that's not the only place you can get them. They're fairly abundant. And if you notice here, I'll draw your attention to the capacity of this particular disk storage drive. Given this disk storage drive, you can store 4,000 gigabytes, which is 4 terabytes. So this one can store 4 terabytes worth of information. That's a lot of data, and it connects via USB, but certainly the faster drives would connect directly to the system bus. And so this is a storage cartridge. They're relatively inexpensive relative to hard drives. Here you have a 5-pack, and this 5-pack, you can store it in raw format or compressed. When it's in raw format, one of these cartridges stores 2.5 terabytes. In compressed format, 6.25 terabytes. So here it is for $129. You can get a 5-pack of these 6.25 terabyte cartridges. That's a lot of storage for just $129. And so that's a simpler standard, but as you go up in your standard here, we see that the higher end storage tapes or storage tape cartridges, here one cartridge can store 12 terabytes in raw mode and a whopping 30 terabytes in compressed mode. So for $124, $125, here it is, you have 30 terabytes worth of storage. That's a lot. And so if you look at the text for this ad, this is from maxsales.com, you see this particular storage cartridge can last for a total of 30 years. So you can imagine 4 of these tapes, one after the other, after the other, after the other, bought in time, would cover a human lifespan's worth of data, right? So you can migrate data just by purchasing 4 of these, and the technology is getting even better. So 30 terabytes worth of storage for $125 is pretty darn good by today's standards. And then more recently, in 2017, there were some breakthroughs. IBM and Sony figured out a new tape standard that can get up to 330 terabytes for one cartridge. That's phenomenal. And so this is the reason why these magnetic tape storage devices are really popular, especially for backup. While they're slow, the massive amount of data that they can store are very useful for doing backups for the increasing volumes of data that we have. So I have 2 links there to articles about storage tapes. And so this is the other predominant mode of storage. It's a magnetic disk. And the disk consists of a set of platters or circles, if you will. And these platters rotate about a spindle. And there are some read-write heads, which are little electromagnets that can read the magnetic orientation of the tracks going around each of the platters. Now, you'll notice here, if I draw a track along the top platter and that same track along the next platter, the same track along the next, you can imagine connecting them together, they form something called a cylinder. And so when we talk about the organization of a moving head disc mechanism, we talk about the tracks, we talk about the sectors, which are along the track, and then we talk about the cylinder, which are a set of parallel tracks going around the circle for each one of these platters. And so when we look at the cylinder, we say, here's the first cylinder, and then they work our way in with these concentric circles to get the next cylinder, and next cylinder, the next cylinder. And so here, this assembly arm can move, positioning these read-write heads over the respective cylinders associated with the particular disc. And then this thing spins and it waits for the sector along the track for that cylinder to make its way underneath the read-write head in order to be read or written. Okay. And so these platters can range in their size up to 14 inches. Now, what is common by today's standards is 3.5 inch, 2.5 inch, and even 1.8 inch. And the density for storage can range from about 30 gigabytes up to as much as 3 terabytes. Now, these days, you can look on Amazon and find it's pretty expensive, a 4 terabyte, in some cases, a 6 terabyte hard drive, and even 8 terabyte. And so the performance, when you measure performance, theoretically the transfer rate is 6 gigabits per second, but effectively when you actually use it, you're going to get about 1 gigabit per second. And the seek time, the time it takes to get the read-write head over to some cylinder, is going to be between 3 milliseconds and 12 milliseconds, and in practice you get about somewhere in the middle, 9 milliseconds for most common desktop drives. Now granted, there are some drives for servers that are much higher performance, but for the most part for desktops on average you're going to get 9 milliseconds seek time, the time it takes to position your read-write heads to one cylinder to the next or over a cylinder. And so the average seek time when we look at it is based on roughly a third of the available tracks that you have on the disk. And then the latency is the time it takes once you get to that track to position that particular sector, the rotational latency, underneath the read-write head. And that's based on the speed of the spindle. The faster the spindle spins, the faster that sector will come whooshing around to be positioned underneath the read-write head. And so that's typically based on the revolutions per minute, the measurement of the spindle speed, and by the calculations, it's typically 60 divided by the RPM. And so the average latency is typically about half the latency of the system based on the theoretical calculation. And so as you can see here from this table, as the spindle speed increases, 4200, 5400, and so forth going up, the average latency is going to go down. Now, of course, the price you pay is power because it takes more current to spin your motors faster in order to get it to spin faster. But you can buy server grade hard drives. They'll be 10,000 RPM or even 15,000 RPM. It'll cost you money because you have to pay for that engineering. Now, of course, if you're looking at low power systems, they tend to use 5,400 RPM for that reason, because less voltage means less power. So the first commercial disk drive took a forklift to load it to a plane to transport. It wasn't something like a cartridge you could put in your bag or your pocket. Now, this is very simple by today's standards, but it was a big breakthrough that you could have reusable mass storage. And this was back in 1956. And so more modern, this is an 8 terabyte hard drive that you can get on Amazon right now. Look this up the day before this is airing. And for about $155, you can get 8 terabytes. So the price has gone down significantly. This is a mechanical hard drive. As you can see here, it's SATA interface, 6.0 gigabit per second. And it's a 3.5 inch platters. And that's what the 3.5 inch refers to, is the size of the platter. And so the price is coming down quite nicely. Now, an improvement on hard drives, it's mechanical, is this solid state disk. It uses all chips to store it. And these chips are non-volatile, meaning that when you turn off the power to the machine, what you have written to this memory, these memory chips, is not lost. And so it's used like a hard drive, and there are many variations on it, and it can certainly be more reliable than hard disk drives, these mechanical drives with platters and read-write heads and arms and spindles, because it does not have any moving parts. But it is more expensive per megabyte. And they can also have shorter lifespan and have less capacity, but they're much, much faster. Their buses can also be slow, so oftentimes they connect directly to your system bus, the PCI interface. And it has no moving parts, so there's no seek time and no rotational latency. It's very, very fast. This is an SSD that you can buy off of Amazon today for about $100. You can get a terabyte, which is much more expensive than the 8 terabytes for 155, but it is faster, and you can see how the price goes up much more dramatically. For 4 terabyte SSD, it'll cost you about $550. So let's take a look at the disk structure. Now, the disk drives, they're addressed and treated as if you have one dimensional array of logical blocks. And this array goes on for the size of the number of bytes that are on your hard drive. So if you have 1 terabyte, that's a 1 terabyte contiguous set of bytes in less logical blocks. And so a logical block is going to be our smallest unit of transfer. And when you have this thing formatted, you create logical blocks on this physical media. And so you're going to treat all of the tracks and the sectors for each cylinder going from the outermost track to the innermost track, from the track on the first platter to the track on the second platter to the track on the third platter, are going to be laid out, all of these blocks, which will be a sequence of which will be your files. And so in this schematic, we have a bunch of files, file A, B, C, D, E, F, and G, and each file is just a concatenation of a series of blocks that, although they look like they're in one dimensional contiguous array that goes on and on and on, they're really mapped to the different tracks, sectors, and platters on your hard drive. And so for the disk structure, we have a one-dimensional array of logical blocks, and that's mapped onto the sectors of the disk sequentially. Now that mapping is done by your disk management system, and sector 0 is always the first sector in the first track, which is at the outermost cylinder associated with the platters for your disk. And so this mapping process proceeds in order through that track and then to the rest of the tracks in that cylinder, and then through the rest of the cylinders from the outermost working its way to the innermost cylinder. And so the physical addressing should be relatively easy until you encounter some bad sectors. You need some way to mark them as bad so that you're not using them, because sectors can degrade, because certainly this magnetic material can have imperfections that can also degrade over time. And so you have a non-constant number of sectors per track. In addition, you also have a constant angular velocity, so the speed at which these sectors go whooshing by is going to be different for cylinder 0 versus the cylinders that are closer to the spindle on the interior. So let's take a look at how disks are connected to your machine. You have a host attached storage, and this is accessed through I/O ports that talk to the I/O bus. And so these things are connected to the system bus, and they set up these transactions. So one standard for connection is Small Computer System Interface, or SCSI. Now, SCSI was very, very popular until it was supplanted by other things like USB 3 and FireWire and fiber channel and things like that. And so SCSI was a bus standard, and you could connect up to a bunch of devices, 16 of them, so-called daisy chained together. And you had one component, which was the initiator, a SCSI initiator, and that requested operations. And you had targets, which were the devices, and you could perform tasks on them. And so each target could have up to 8 units, and these were the disks that were attached to the drive controllers. Supplanting SCSI was something called fiber channels, called fiber because fiber optic communication. It's very high speed architecture, and it has a switching fabric, so you can switch units of data across it and address these devices uniquely. And so with fiber channel, you can build a lot larger connection among storage units, and these are called storage area networks, or SANs. And you can have many hosts on fiber channel attached to many different storage units pushing their data back and forth appropriately through these 24-bit switches. And so I/O can be directed to a certain bus, a certain device, arbitrarily using an addressing scheme that is beyond the scope of this particular course. Um, so what this enables, which is nice, is this idea of a storage array. You can just keep attaching disks or arrays or sets of disks, and each storage array is going to have its own controller that gives you certain features for any host that can attach to this particular network or communication mechanism. And so you have ports that you use to connect the host to the storage array, specialized ports, and then you also have memory and software that controls the actions. And you can have as many as thousands of disks, and you can also have them in configurations that give you redundancy features in order to make sure that your runtime is as long as and uninterrupted as possible. You can also have shared storage, so this will make things much more efficient in the storage array, arbitrarily attaching hosts and detaching hosts, and they can bind themselves to use certain storage devices as they need in order to store and retrieve data. And so you can also add with storage array certain features that add reliability and desirable properties for having stable, reliable data that you can have recall, store and recall when you need. And so this includes things like snapshots and clones and replication and things like that, which again are beyond the scope of this class. And so this schematic is in the book. It's a depiction of a storage area network, and this is common in very large environments like a data center. And in this, you have multiple hosts that are attached to multiple storage arrays. And so you have your storage area network off here on the left. You have a bunch of storage arrays, and you might have a tape library in order to back all this up. And then you have some servers and data processing that are attached to a network that clients make requests to, and they all attach to these target devices in order to retrieve and to modify and store data on the storage array. And so a storage area network is one or more storage arrays that are connected to one or more fiber channel switches. And these fiber channel switches are responsible for pushing data around from one part of the storage array to other parts of the storage array. So the hosts machines, the servers, also attach to these switches, and storage is made available through an addressing scheme, logical unit masking, or LUN masking, to get data from specific arrays to specific servers. And so there's a whole addressing and switching scheme, as well as an identification mechanism for how you're going to push data or route data around the storage array from the device that has the data to the host or the client that's requesting the data. And the storage area network makes it very easy to upgrade. You can add or remove storage, add or remove hosts. It makes it much easier, it's dynamic. And using fiber channel, because it's so high speed, you have low latency, and so the access time is very nice. And so one of the questions you might ask then is why have a separate storage network versus a communication network between your hosts? And so NAS, network attached storage, was developed to integrate everything into one system instead of having two separate communication domains, one for storage and one for application networking. And so network attached storage is a type of storage made available over a network instead of a local connection, this high-speed system bus like fiber channel. And so this allows you to remotely access file systems. And two very popular methods for network attached storage is NFS, which was created by Sun Microsystems, Network File System, and Common Internet File System, or CIFS. And these are still out, very popular today. Now, in a network attached storage, or NAS, you have your clients, and then you have your local area network or wide area network, and then you have your network attached storage here, and they're addressed using TCP/IP, and the client pushes data to them or pulls data from them. And so these are implemented using remote procedure calls between the host and the storage, typically underlied by the popular protocols for the modern internet, TCP, Transmission Control Protocol, or UDP, Unreliable Datagram Protocol, over IP, which is the addressing scheme for how you route from one machine to another. And then there's also something called iSCSI, which is an internet protocol-based version of SCSI, where you use the TCP/IP network to carry the SCSI protocol packets. You can remotely attach the devices, examine their blocks, read their blocks, write their blocks. And so it's a type of SCSI, but the protocol, instead of over the custom SCSI bus, it's going over TCP/IP networks. So let's take a look at disk scheduling. And so typically, the operating system is certainly responsible for using or making efficient usage of the hardware. Now, for disk drives, this means that you want to make access time as small as possible for the disk and increase the bandwidth, the amount of data trafficking onto and off of the disk. And so this usually boils down to minimizing the amount of time spent seeking, moving the read-write head to the correct cylinder on that disk. And so seek time is often translated as being seek distance, how far away the cylinders are that you're going to seek to. And so disk bandwidth is the total number of bytes that you transfer divided by the total time between the first request for service to get data or write data and the completion of the last transfer. And so the name of the game in disk scheduling is to try to increase efficiency and also minimize the time it takes seeking. So there are many sources of this request for I/O, the demand on the disk drive. The operating system can do it. System processes can do it, and user processes can request I/O. And this typically includes whether or not it's input to write data to or output to get data from. As well, it includes a disk address, which disk, a memory address, because remember you're setting up a DMA transfer to transfer a block of data from the I/O buffer for the disk device to some memory, some page in memory. And also you need the number of sectors that you're going to transfer, because the number of sectors is how much data on the disk you're going to input or output. And so this is the I/O transaction, and the operating system is going to maintain a queue of requests, one per disk or device. And so whenever a disk is idle, it can start working on its I/O requests. And if a disk is busy, it can not work on a request, and therefore it has to queue up all the incoming requests that are the I/O demands of it from other parts of the system. And so you have a number of optimization algorithms that only make sense when a queue exists, and those are your disk scheduling algorithms. And so you note then the drive controllers, they also have some buffers, and they can manage a queue of I/O requests of various depths. Some of them can handle large number of queued up requests, some can handle only a small number. And there are several algorithms that try to schedule the servicing of these disk I/O requests. So you have these requests, they're queued up, and the selection mechanism for which request you're going to take is your disk scheduling algorithm. And so this analysis is true whether you have one platter or many platters. And we're going to look at scheduling algorithms where you have a request queue, and this request queue concerns cylinders numbered from 0 to 199. And so here we have a string, and that string is the request for cylinders. And we count the number of cylinders over which the read-write head traverses when it's going to satisfy a read or write operation for some track in that cylinder. And so we start out that the head pointer corresponds to cylinder 53. And we have that same string, 98, 183, 37, and so forth, which are the cylinder numbers associated with the I/O requests. And so our first disk scheduling algorithm is going to be first come, first serve. And what this illustration shows, you'll see, is a total movement of the read-write head over 640 cylinders. Now, that doesn't mean that you have a total of 640 cylinders. It means that as it moves, it's going to go over a total of 640 cylinders. And so we have our request queue and the head starting at position 53 over cylinder 53. And so first come, first serve says, okay, well, it goes to 98. You can see 98 is that first cylinder request, and it's going to seek from cylinder 53 to cylinder 98. Then it's 183, goes to 183. And it takes it in a first come, first serve order. And here's our queue. There's the head of the queue, and here's the tail of the queue. And these are the requests, i.e. the cylinder numbers associated with each disk transaction for disk I/O. And so we notice if we go across, and then after 183, it's 37. So it comes back and it spans from 183 to 182 to 181 to 180 and so forth until it seeks to cylinder 37. So then it goes to 122. And so we count here for the performance. We look at the number of cylinders that it has traversed, the read-write head, when it's satisfying the requests for cylinders for transactions from this request queue. And so that's first come, first serve. Now, another approach is so-called shortest seek time first. And what this does, it orders these cylinders for the request based on the minimum seek time from where the current head position is. And so this is a form of shortest job first. If you look at it, it says, okay, if I'm going to satisfy a request, I'm going to take one with the shortest job, shortest burst time. In similar fashion, for disk scheduling, I'm going to take the request that is associated with the shortest seek time, or the one for a cylinder that is closest in distance from the current cylinder where the read-write head currently resides. And so this can introduce some starvation of some requests, but nonetheless, shortest seek time first is a different disk scheduling algorithm from first come, first serve. So if we look at the total head movement over the cylinders, we again start at cylinder 53, and shortest seek time first. Okay, the first one is 65, that's closest. So there's our 65, it's closest to 53. So we go to 65, and then from 65 to 67, to 67 to 37, 37 to 14, and so forth. And so when we do this, shortest seek time first, you'll notice here that the total head movement over the cylinders is dramatically reduced to 36. When we looked at first come, first serve, it's a total movement of 640 cylinders that it traverses past. And now we've cut that dramatically down by changing the order in which the scheduling algorithm attends to requests for read or write, i.e. the cylinder numbers in the queue. Another one is called the scan algorithm. And with the scan algorithm, the disk arm starts at one end of the disk, moves towards the other, servicing requests along the way till it gets to the other end. And then the head is reversed in its movement. And so, in effect, it's scanning back and forth. And sometimes the scan algorithm is called the elevator algorithm in the research literature or in the literature in general, because like an elevator, it goes all the way up and then all the way down. And then as it's going up, it services requests it gets along the way. As it's going down, it services requests along the way. And so an illustration of it shows a total head movement of 236. But if these requests are very dense, meaning there are very many of them, the largest density at the under end of the disk, those wait the longest. And so you could have a large wait time with scan if you have a high density at the opposite extreme of the disk. And so this is an example of scan algorithm. Again, we have the same request queue. These are cylinder numbers, and the read-write head starts at 53. Now, of course, it goes from 53 all the way to 0, taking care of all those requests it encounters along the way. So as you go from 53 towards 0, there's 37, there's 14, and then you get to 0, and then you reverse direction going the direction towards 199. When you go from 0 to 199, there's 65, you have 67, you have 98, 122, and so forth. And so the scan algorithm, it tries to make the wait time more uniform more uniform. It tries to decrease the wait time or make it more stable so that you don't get this idea of starvation that you had with the shortest seek time first. And so this scan, there's an improvement on scan called C-scan. And C-scan produces more uniform wait time than scan. And so with C-scan, C stands for circular. The head moves from one end of the disk to the other, servicing requests as it goes along. And then when it reaches the end, it immediately returns back to the beginning without servicing any requests on the return trip. Now, this might seem non-intuitive, but essentially it treats the entire disk, all the cylinders, as if it were a circular list and wrapped around. But of course, you can't really wrap around in practice. You have to literally seek back to the other end and then make your way across again. And so when we look at C-scan, the circular scan again, so we're scanning in the direction of cylinder 199. We start at cylinder 53. So we're going in an increasing direction. So we go 53 to 65 to 67, 98, 122, 124, 183. And then we continue to go to 199. we don't have any requests. And then all of a sudden, we circular return back to the left-hand edge to cylinder 0 on the outer edge of the disk, the outer track, and then we work our way again towards cylinder 199. And there's the C-scan. Now, of course, one of the big slowdowns with C-scan is that we jump from 199 all the way to 0. We're seeking, and we pay that cost every time we want to wrap back around again. But the good news is for C-scan, it makes the wait time much more uniform rather than this idea that you can have starvation. All right. So there's another one called look, and look is a version of scan, and clook is a version of cscan. Now, of course, with the look version, both the clook and the cscan look versions, the arm, instead of going to the extremes of the cylinders of the disk, from the outermost cylinder all the way to the innermost cylinder at the other end, the arm only goes as far as the last request in each direction, and then it reverses direction without going all the way to the edges of the disk. And so when we look at the total number of cylinders it traverses for the clook, we have an example, and this is from the book. We start at cylinder 53, we go to 65, 67, and we go in that direction towards 199, but we stop at 183 because that's the most extreme cylinder that we've gotten. We don't go all the way to the edge of the disk, and all of a sudden we do that circular part. We go all the way back to the 14 because 14 is at the other extreme. We don't stop at 0, and then we work our way back to the right again towards cylinder 199 from the outer cylinder to the inner cylinder, and we go from 14 to 37. So this is a circular in that we're traversing all the way back and only going in one direction when we encounter these requests for disk I/O. And then the look part is that we're only considering the extremes for the actual requests for cylinders rather than going to the extreme boundaries of the disk from cylinder 0 to 199 and then reversing again. And so when we select a disk scheduling algorithm, shortest seek time first is very common and has a natural appeal, but scan and cscan can perform better if a system places heavy load on the disk, because you have less starvation that leads to better performance. So this idea of making the wait time more uniform, more stable, has benefit if you have a lot of heavy usage of your disk. And so the performance then depends on the numbers of the requests and the types of requests, and requests for disk service can be influenced by the way that you allocate files. It's all about the layout of the directory structure in the files, the so-called metadata for your disk system. And so the disk scheduling algorithm certainly should be written as a separate module from the operating system, and this allows you to replace your scheduling algorithm to impact dramatically the performance of your operating system based on the work set and the application load and application workflows that you might be running. And either shortest seek time first or look is a reasonable choice for your default, but you could certainly change it quite easily if you have the disk scheduling algorithm written as a separate module that you could swap in and swap out when you want to change something. Now, of course, rotational latency, or the latency, the amount of time it takes to spin that platter to line up the cylinder that you need from that, the sector that you need from that track under the read-write head. That's difficult to calculate because it's depending on the amount of time it takes to speed up the spindle, to spin up and spin it down, and there's a lot more difficulty in those calculations. So there's a lot more difficulty in those calculations. And so disk-based queuing is going to affect your operating system performance. And so it's really, really important to be careful about how you're scheduling your disk operations. So let's look at the management of your disk. And so when you're trying to manage your disk, we look at the low-level formatting. We also consider what happens to the physical layout, this mapping between this logical, one-dimensional tape, if you will, of blocks and how it's spread out among the tracks and sectors on your disk and the cylinders. And so we take a disk and we divide it into sectors, and these sectors can be read or written by the disk controller. So each sector is going to hold a bunch of information. One of them is header, which is descriptive information used by your file management, plus data, and then some error correcting pieces, some error correcting codes to try to recover from bit errors. And so usually you have about 512 bytes of data for your sectors, but this can be tunable. They can be bigger, they can be smaller, depending on how you format them. So in order to hold files on a disk, the operating system still needs to record some of its own accounting on the disk. And this includes something called a partition. Right? What a partition represents is you take your disk and you divide it up into one or more groups of cylinders, and each cylinder is treated as if it were a separate logical disk. And so when you do logical formatting or making a file system, what you're doing is you're increasing the efficiency by taking each one of these and grouping it up in blocks into what are called clusters, groups of blocks. And so this partitioning says, let me take a subset of my cylinders, whereas the logical formatting, the making of a file system, is taking those sectors and putting them together into clusters or blocks. And this is done for I/O, and therefore file I/O can be done in clusters. So when you're going to write a file, you write them as clusters and not just as individual blocks. And so you can also, for certain specialized applications, give raw access to some applications like databases, and that keeps the operating system out of the way, because who better to make use of the file system than the application itself that needs that specialized access. And so you also have something called a boot block, and this boot block is responsible for initializing the system. The bootstrap is stored in ROM, and it starts out and wants to execute something called the bootstrap loader, which is located typically in sector 0, track 0. And this bootloader program, it will boot blocks of the boot partition and do things like load your operating system. And so there are certain methods such as sector sparing that's used to handle bad blocks. It just says, okay, let me mark this thing as bad, and I will just ignore it and make it off limits. And so in Windows, when you partition, let's say if you have 4 partitions of your disk, remember a partition is nothing more than a subset of your cylinders treated as if it were a separate disk. And then you have your master boot record, which is on cylinder 0, track 0. You have your boot code, and then you have your partition table, which has that logical accounting information needed. What are the subsets of cylinders, and what partitions do they refer to? And so when your boot code runs, it says, okay, well, I'm going to go to a certain partition, and I'm going to boot from there something like a particular operating system that happened to be stored in that subset of cylinders for that particular partition. In this case, the figure which is in the book, it's partition 3. So let's take a look lastly at swap space. And again, we said swap space is used by the paging system, virtual memory, to offload chunks of processes from frames, their pages from frames, in order to free up frames for use by processes that might need them. And so for swap space management, swap space, virtual memory uses your disk space as a type of extension of your main memory. And so as memory capacity increases, swap space is less needed, but in many cases, most operating systems today, you're going to set up some kind of swap space. And so swap space can be carved out of a normal file system, but more commonly, it's a separate disk partition, a raw partition that's set aside for swap purposes, your so-called swap partition. And so for swap space management, different operating systems manage them differently. BSD, it does it when the process starts. It holds the text segment, which is the code of the program, and the data segment. And the kernel uses swap maps to track swap space. So the kernel certainly uses a lot of buffers, and it's going to use a lot of swap space for its purposes, and it's going to track them. Solaris, it allocates swap space only when there's a dirty page that needs to be written out. When something has been updated and you want to swap out, that's when you make use of swap. And so file data is written to swap space. It's deferred until you need to write the file, right? And other dirty pages go to swap because there's no other place to put it. And then things that are read-only, like your text segment that has your code, that's thrown out because it's more efficient to reread it from the file system. And so this figure is in the book. It's a schematic that looks at your swap space, swaps area is broken up into partitions, and it maintains a swap map. This is for Linux, and a swap map represents how many processes are using that particular page that's in the swap file. And so, for example, here in our swap map, we see that there are 3 processes that are using this particular swap area, that particular slot for pages in your swap file. And so this reference counting is how Linux system manages it, because it needs to know, and it maintains, at least the kernel does, how many processes are using a particular partition, because once that reference goes to 0, that means no process is using it, and so it's effectively reclaimed. Okay, and so lastly, RAID, redundant array of inexpensive disks, which I will not cover this year's cohort. It's a way of increasing your reliability of disk using a lot of disks, a high number, that do things like store backup copies and store parts of the data on different disks, and to do things like error correction to increase the reliability of storage. And so RAID is another really important aspect of mass storage, but we're just not going to cover it this semester. All right, so with that, that's all I had. Again, please make sure you're keeping up with the reading, and make sure you are aware of these key dates. And that's all I had for today. Happy Thanksgiving. Please stay healthy. Please stay safe, and enjoy the Thanksgiving holiday and travel safely. So with that, we'll end there, and I'll see you all on Tuesday.